right, here we go. We have a buffered solution here. They gave us a KB. They want us to calculate the pH. Okay. So we need to figure out our Ka for this guy. All right, because we need our Ka value for the equation. Remember our equation from last week where we had our H plus equal Ka, and then we had the concentration, or it could be moles. We could use moles here too. Either way, that's our acid over our base. Okay, remember that from last week? But this requires that you use a Ka value. So we need to get our Kb to be Ka. So if I take this and I do 1 times 10 to the minus 14 divided by the Kb value, that's going to give me a Ka, and I'm solving for H plus. So if I take this divided by this, that's going to give me my Ka, which ends up being 5.6 times 10 to the minus 10. Okay. Then I need to take my acid and my base. So I've got to figure out which one of these is my acid and which one is my base. What is this?
That is a base.
Base, and this is my acid. Okay, good. Okay, so the molarity of my acid is here. This is my acid, so that's 0.40 divided by my base, which is 0.25. Now, how do we know that one was the acid and one was the base? Okay. This is NH3. This is NH4. Which one has more hydrogen? This one. That's my acid. It's as simple as that.
So that's the answer.
Well,
Oh, I thought there was too far.
well, I've got to multiply. I've got to divide this and multiply it out.
I thought there was two.
You know, all we had to do was circle.
Yes, that's what we had. Ellie, that's not.
So 8.89 times 10 to the minus 10. That's my H plus molarity. That's not what they wanted. They wanted pH. Okay, so I'm going to take the negative log of this value. When I take the negative log of that value, I get 9.05.
You're thirsty every single day.
Okay, now.
Water bottle.
I'm poor, Evie. I don't have running water.
You
Thank
do. You do have the water
Pens.
bottle.
I'm going to separate you. All right, now we're taking this and we're adding in 0.1 moles of HCl. Is this an acid or a base?
That would be
Acid.
an acid.
An acid, okay? So I'm going to take this equation that I had up above. Now, for this equation, we have to have stuff in moles, okay? And it's a 1 liter solution, so it's fine. So 1 times 0.25 is still 0.25. And 1 times 0.4 is still 0.4. So I've got those in moles. Did you see how I did that?
Yes.
Okay. Now, this is an acid. So what are we going to do? Add it. So we're going to do plus 0.1. And our base, we're going to minus 0.1.
Add 0.1. Subtract. Okay.
Do the multiplication. Do the division. You end up with 1.87. Congrats.
What'd you do?
Times 10 to the minus 9.
Yes.
Which means the pH then, if I take the negative log of this, the pH is going to be 8.73. Okay? Does that make sense? When we added acid in, our pH went down. Is that rational?
Yes.
Because
Yeah.
it gets more acidic.
Okay.
Acidic goes down.
What if it was like 500 milliliters of filtered solution? Would you just multiply by?
So if it was 500 mils, you'd have to get this into moles. So you would take 0.25 times 0.5. So then this would be 0.125. Good. All right. Easy enough?
Yeah. Is this still the easy part of this?
Yep.
Can you pass me the
All right. We've got a chemist here. They needed a buffered solution at a pH of 4.3. They can choose from these acids. They want to know which one to choose from. So what I did was I took these and I did negative log of each one. So negative, oh, my battery's dying. All right, there we go. You should be happy now. Okay, there we go. So I've got negative log of 1.35 to the negative 3. And this is going to be 2.87.
I know.
Negative log gives me the pKa. So hey, hens, that is enough. Negative log of this gives me the pKa, and I'm trying to find a pKa that is close to my pH. So this one ends up being 4.87.
Oh my goodness, hold on, I can't keep up with this.
To the pH that we're wanting, yeah.
There's one that's closer, right after this is 4.2. Who was saying that?
Hey, that did not sound like you.
Yeah, it did not.
Sound like you.
I think.
Smart, intelligent.
Yeah, I almost have them all. This is really.
All right, this one is 4.19. And this one's going to be, you can tell this one's going to be way off because it's to the negative 8. So I'm not even going to waste my
I'll
time
tell
with
you
that.
what it is.
Okay.
7.46. Did you get that? I just needed to have one with Ellen.
7.4.
You sound like hell. I need to tell you
All right. If I take 10 to the negative 4.3, that is going to tell me what H plus concentration I want. Okay. So my H plus concentration here is going to be 5.01 times 10 to the minus 5. And that's going to be equal to my Ka, and we said that we liked this Ka best because it was closest to this 4.3. Okay. These two are very close to one another, so that is why I picked that one when I did my pKa. Okay. So I'm going to put in 6. No, that's not right.
that's right. Stop it. Can't say that.
Why did I not select that one?
I'm actually confused.
87 minus 4.3. Yeah, that's way further off. Why would we select that one? It's weird. All right, well, we'll go with it. All right, so 6.4 times 10 to the minus 5. And then that's the ratio of our acid over base, right? And this is what we're trying to figure out here. Okay, so this, yeah, so I want to figure out what that ratio is. How do I get this by itself?
You divide by 6.4.
Right, so I'm going to divide both sides by 6.4 times 10 to the minus 5, and that's going to give me my ratio.
Oh my goodness. So 5 divided by 6. 0.4. Something like that.
Okay, makes sense? Everybody cool with that?
I'm with you. Because I just needed, where did you get 10.43 from?
10.
10 to the negative.
Oh, right here. This is the pH we want.
And then you.
So this is the pH we want. So if I do 10, hey, if I do 10 to the minus 4.3, that gives me my H concentration. Okay. And then I put that equal to the Ka that we selected. So we took all of these Kas and turned them into pKas, except for the last one. And we could tell from looking at that one, it was 10 to the negative 8. Like that's going to be way out of the ballpark. So I just eliminated that one. I didn't even bother wasting our time with that. So I just got rid of him right away. But this pKa here was closest to 4.3. So I use that as my Ka value. Remember, our H plus equals our Ka times our acid over our base.
Our H concentration is equal to our K value divided by acid over base.
Yeah, that's what we talked about all last week, or last Friday. Remember, I told you to go home and memorize this equation?
Oh my god! Oh, that hurt so bad!
I'm sorry, I can't hear.
Are there any specific conditions that need to be met for this to be true?
You need to have a conjugate acid or base and its salt. A weak acid or base and its conjugate.
Weak acid or base with a strong acid or base.
Well, you're going to be titrating those things, but yeah.
And this works along the entire pH curve.
Yeah. All right, speaking of curves, weak acid, strong base, your pH is going to be greater than 7. Strong acid, weak base, pH is going to be less than 7. Remember, if it's a strong acid, strong base, the equilibrium point is, if we did a strong acid, strong base, where would our equilibrium?
7.
Exactly at 7, right? Okay. There is a distinction between equivalence point and endpoint. The endpoint is where the indicator changes colors. Typically, you're past the equivalence point when that happens. Okay. For the titration, then, if we had 50 mils here of NaOH and nitric acid and NaOH, they want to calculate the pH of the solution at the following points. Okay. We don't have any NaOH added in. So at that point, it is just going to be this guy. All you have to do is do negative log of 0.200. And that'll give you your pH. That one's easy. Wait a minute. What did I do? Negative log. Looking at the wrong thing. No, that's fine. Yeah. All right. So negative log of this gives me 0.70 for my pH. Okay, because they want to know the pH of this. All right. 0.1 mils of NaOH has been added. Now, the thing about this is not a buffer problem. Why?
Because it's adding something that was already in there.
Nope.
Because you're adding base, not an acid.
What did I just tell you had to be present in order to have a buffer
Wait, hold
solution?
on. It's both strong.
No.
Nope.
Weak acid or base and its conjugate salt. Okay. These are both strongs. Okay. So if they're both strongs, this comes down to a stoic problem, not a buffer problem.
I like soy.
So we tell by knowing if they're both strong acids?
Yep.
Okay.
What's the difference
Yeah,
between
yeah.
a stoic problem and a buffer problem?
No, it's 0.7.
Buffer problems, you're going to use this.
And that's defined the H concentration?
Yep.
And K concentration.
Or Ka. Ka is not a concentration. Your equilibrium constant.
No, we.
All right, these are both strongs, so this is going to be a stoic problem. Okay? Which means we need to get what goes in our table.
Water. Good job, Allie.
What do we have down here? It's a BCA table. Only what in the holes?
Moles.
Only moles in the holes. We got to get these into moles. Okay. So our H plus concentration, which is this guy right here, we need to get that into moles. So 0.5 times 0.2 is what?
0.1. Wait. 1. It's 1. No, I was right. Oh my goodness. This is so hard.
Okay. For this guy, we're going to take this molarity, which is 0.1, and we're going to multiply it by 10 mils, but it can't be mils. It has to be
0.01.
0.01.
So this is 0.001. Okay.
So OH is the limiting reactant.
Yep. So we're going to minus 0.001 here. We won't have any of this left over. This we're going to have 0.009. So if we take, remember these are moles. We need to divide it by liters. How many liters are we up to now?
50? No, 60.
Liters?
0.06.
It's
0.06.
No, wouldn't it be 0.099?
Or
No.
is the H plus
Yes,
concentration?
it would.
point-
That's minusing. That's not minusing.
Or was the H
C.
plus?
We're looking at
concentration?
liters, Evie.
No, for the H plus, it was 0.1 minus 0.001 is 0.099.
Is the H plus concentration supposed to be 0.01?
2 points.
because
Yeah, this is 0.01. Ah, crap. All right, so if we had 0.2 times 0.05 is 0.01. That's where I got off, was right there. All right, everybody's up with me now?
Yeah.
I think I've fixed all my errors. All right, so this is 0.15 molar H plus. So if I take the negative log of that, that's going to give me my pH of 0.824. Does it make sense that we've gone from 0.7 to 0.824 when we've added base in?
Yes.
yes, because it takes
Base
away
goes
less
up.
acidity.
Okay.
Oh my God, sorry, I didn't mean to say it.
Are you sure, I've called police on you.
All right, I'm gonna try to do this one right this time.
So this is the same type of thing,
Yep,
just more.
I'm just adding more right here. All right, so this is going to stay the same because we're not changing our acid. We're just changing our base. So now we've got 0.02 times 0.1. So that's 0.002 here. So minus 0.002.
That euro is like one.
Yep. So now I'm going to take 0.008 and divide it by what?
Divided by
0.07.
70.
0.07 liters.
Okay, so that's going to, and this is still H plus, so this is going to give me my H plus concentration. And when I do that, I end up with 0.114. Should my pH be less than or greater than?
Greater than.
Greater than, yep. And it does. It turns out to be 0.942.
Oh, you were right.
Oh, shoot. This is not. So what does it mean total as opposed to additional? Like adding 20 as opposed to additional. Like what's the difference?
So total, if it was additional, then we would be at 30 mils of NaOH. So if it was additional, then we would have added 20 to this 10 that we already had, but it's total, so it's 20 mils total.
So if it was additional, we would add the 50, the 10, and the 20.
Yeah. And this here would be 0.03 instead, because you would have added 30 mils of this. 0.003, excuse me.
What's the difference between an ice table and a BCA?
So this is a BCA table, okay? BCA tables are for stoichiometry, and they are for, you should only have moles or liters of gas. You can do liters of gas because 1 mole equals 22.4 liters of gas. So these, you use that. When you're figuring out what's going on, your limiting reactant, that sort of thing, you're going to use your change section here to figure that out. Okay. So I talked about to my kids, I'm like, that's going to create your cloud. That's the way I taught it. For ice tables, then you're typically you're going to have initial change in equilibrium, and you need molarity in there.
So only molarity for ice table.
Yep. No, not only. You could have pressures. So concentration, pressure, but typically those two things.
But besides, like,
So whatever your K value is, if it's Kp, it's going to be pressure. If it's Kc, then it's concentration. If it's Ka or Kb, then it's going to be concentration as well, because that's, concentration of acid or base.
for ice tables, only for finding the K value.
For equilibrium, yep. Well, I mean, sometimes you have the K value and you're trying to find, the other parts of the, sometimes you have the K value and you're trying to figure out what the new concentration is going to be or what it started out as. But you should never use an ice table if you have an arrow that's going this direction. In order to use an ice table, you should have an arrow that's going back and forth because you're at equilibrium. If you have an arrow like this, and that's what these are. These are straightforward arrows. So that should be like an indication to you right away. It needs to be stoic and not ice. Sometimes you'll also hear them referred to as rice tables, which is reaction. So our reaction is listed here. and then initial change equilibrium. All right, here we've got 50 mils of NaOH added. Now, this seems to you like this is going to be your equilibrium, right? Because you've got 50 mils of NaOH and you've got 50 mils of this.
Wrong.
Why?
Concentration.
Right, your molarity is different. So if you had the same molarities here and the same volumes, that would be correct. But in this case, that's not. So don't let your gut instinct kind of fool you there. Okay. So here's my
the same, right?
H plus OH. Yep, same thing. H2O. This is still going to be 0.01. This is not changing throughout. This is going to be what?
0.005.
0.005. Okay, so now I'm going to subtract 0.005 from here. I'm going to subtract 0.005 from here, leaving me with 0 and leaving me with 0.005. All right, now I got to take that over, 0.005. I'm going to divide it by what?
0.101.
Not 0.01, 0.1, because it's 100 mils. 0.01 is 10 mils.
Oh my bad. Yep. Whoops.
Okay, and then when I'm there, that gives me 0.05. And again, this number should be greater than or less than this.
Greater.
Right, so it's 1.3 is what it ends up being. And how I figured that out was I took the negative log of this value. So negative log of this gives me a 1.3 pH. All right, now we are at the equivalence point. Okay, so because I've got, if I do this, okay, so let me prove that to you.
You can
Okay.
double the number, right?
So here I have 0.01 of this. This I have how much now? What's my moles? I got this times 0.1, so that's 0.01. Okay, because that's 0.01 here for my liters. If these two are equal and this is key, and it is a strong acid, strong base, then that means that your pH is equal to 7. And we don't need to do any more math, any more calculation, any more beyond that. Okay. Now we are going to add 200 mils total of NaOH here. So H plus OH minus yields H2O. So here I am at 0.01. Here I am at 0.02. So this time I'm going to have this stuff left over, the OH, and I'm going to have 0.01 molar of that left over. So this is 0.01 molar OH minus. So if I take the negative log of that, what's it going to give me? Yep, it'll be something above, well, no, it won't be actually. Negative log of this will not be above 7. What is it going to, if I take the negative log of this, what does that represent? POH, okay? And that's going to equal
2.
No.
That's what it said when I typed it in.
Oh, here's my problem. Uh-huh.
0.01 divided by 0.25.
Okay, now, that's going to equal 0.04. And if I take the negative log of that, it's going to give me POH, which equals 1.4. Right, the pH then is going to be 12.6. So 14 minus this gives me 12.6. Good times?
Good times and line should be.
Don't tan mines. I don't tan.
I do.
All right, now we get into the fun. That was easy. That was just too easy. All right. We're getting out of the land of stoic. We're going into the land of buffers. So pH, before the titration begins, treat as usual. The acid or base in the flask determines pH. If it's weak, you have to use the Rice tables. pH, on the way to the equivalence point, then you're in the land of buffers. So if you're in the land of buffers, you're going to use this equation.
And how do you know if you're in the land of buffers again?
Do you have a weak acid and its conjugate base? Or a weak base and its conjugate acid? And how do you know if it's a weak acid or a base? It's not strong. And you have those memorized.
Is it conjugate base a weak acid, a strong base?
It could just be a salt. So it could be like potassium chloride or something.
Libby, let's just save this for tomorrow.
All right, so pH at the midpoint of the titration is your half equivalence point. Remember that your pKa equals your pH at that half equivalence point. So that can be helpful. pH at the equivalence point, you're simply calculating the pH of the salt or the acid, which is now neutralized. So you've got to look at, is it acid salt or basic salt? pH beyond the equivalence point, it's usually stoic again with the limiting reactant. And then you're going to calculate the molarity of the excess and solve for either pH or POH and then convert. We've talked about this salt hydrolysis, these reactions. We've talked about, so hydrolysis is where you're splitting your water, okay? The rest is much easier if you think of it as HOH instead as a reactant. So essentially a hydrolysis reaction is where you are taking, it's the reverse of a neutralization reaction, and it's written in the net ionic form with a soluble salt. If a strong base is reacted with a weak acid, strong wins. The salt is basic, thus OH forms. If a strong acid is reacted with a weak base, strong wins. And the salt is acidic, and we've talked about that. I've showed you how that works. The strong portion of the acid or base is the source of the spectator ion, and the remaining ion then is the reactant that reacts with water. Okay, so hydrolysis reaction for NaCN, so sodium cyanide. First, recognize that sodium cyanide as a salt, that if that information is not given, the polyatomic ion is a dead giveaway. Next, ask yourself which acid reacted with which base to generate the salt in the first place, which base would have been NaOH, with which acid would have been HCN. Right? Because the CN is negative, that's going to go with a positive. This is a negative, so it's going to go with the positive hydrogen. The Na then is a positive, so it has to go with the negative OH, or come from that. They're asking about where it comes from. Now ask yourself, is the base strong or weak? Strong. Is the acid strong or weak? Weak. So strong wins. So your pH at equilibrium is going to be
Above 7.
above 7. Right. All right. So start the same way every time. You write a hydrolysis reaction. You're going to draw your line here. It's water. So water is going to be breaking apart. It's a basic salt. So you've got your CN. That's going to go to OH over here. And then you're going to give off HCN. So hydrolysis reaction is what you must plop into then your Rice table to solve for either pH or POH, because at equivalence point, the moles of acid equal the moles of base, which equal the moles of salt formed. Just be sure and calculate the molarity of the salt by tracking the total volume before putting its concentration into the rice table. All right, so here they want us to write these reactions. All right. So K, is that strong or weak?
Strong.
Strong, because KCl, right, or I'm sorry, KOH is one of our strong bases. So we're going to ignore that right now. We're going to focus on this. So this is my NO2 minus. It's going to come together with water. And it's going to form what? What is this going to grab from my water? The H, right? Because this is a negative, so it needs to grab the positive water. And if you think of this like this, it might even help you a little bit. HOH. This is going to grab this H here, form NHNO2, plus it's going to leave behind OH minus. All right? Which one of these two things do I get rid of? The NO3, because HNO3 is strong. So that's, and I guess I can go down here and write, so I have a little more room. So now I'm going to take my NH4 plus HOH. What's it going to grab from here? The OH, leaving an H behind. So H plus NH4OH. All right, C. Is it going to grab this or this?
CL. It's gonna grab CH.
No,
Right.
CL.
Cl's going away. That's my strong. Remember, HCl is strong. So it's going to grab the CH3NH3. And what charge does that have?
Water.
Positive. Plus HOH. What is this going to grab from here? The OH, because the OH is minus. So CH3NH3OH plus H plus. All right, what am I getting rid of here?
ClO2.
Na, because NaOH is strong. So my ClO2, what charge does it have?
A negative.
Negative. Plus HOH. That's going to yield. Oh, that's an ugly yield sign. Sorry, y'all. What's it going to grab from here? H plus, right? So it's going to form HClO2 plus OH minus.
So the weak acid or base always reacts with the water.
Yep. Because the strong is just going to stay as ions. So if Na gets in and like the OH is left behind, it's not going to join up with that OH. You're just going to have Na floating around and OH floating around. It's not going to make anything on the other side like these do. But remember, your weak acids and weak bases, okay, so these are weak bases, these are weak acids, they are going to stay together, okay, because their Ka values are less than 1. So they tend to stick together. So you're still going to have a little bit of OH in there and a little bit of H plus generated from this reaction. Because these are grabbing a hold of that and forming either a weak base or a weak acid.
Are those salts on the product side?
This would be the yeah, this is a salt. No, this would be the salt. This is the salt here. Yeah, these are the salts on this side.
So would they be like precipitates?
No, usually they're ions. Most of these, because I mean, this is ammonium. Yeah, they're going to stay as ions. They're going to be floating around.
The the parts of like NH4, HMC.
This is a base because it's an OH.
So is it still like dissolved?
Yeah, I believe so. Yeah, I mean, it's going to be floating around in there, but it's going to be floating around as the acid here.
As one molecule?
Yeah. Yep. All right, we're going to finish this up tomorrow, you guys. I think I gave 3 days for buffers, so.